Hello everyone, welcome to the session Introduction to Time Series Data Analysis with Python. We are joined by Manik Fernando, who is a senior machine learning engineer at Search Global, and he is contributing to develop products that leverage machine learning for over 4 years now. He has a Bachelor of Science degree as well as a Master of Science degree obtained from University of Monaco. Manik, it's a pleasure and a privilege to welcome you to this session, and I will hand things over to you.
Thank you, Tiara. Let me share my screen. Can you see the presentation?
Yes, we can.
Thank you. Thank you for having me today. Thank you for the organizers. Today we are going to talk about time series analysis using Python. To start things off, I think it's kind of important to have an idea of what time series means. What is time series data? So I think some of you might have some understanding of what usually a regression data set means. So that means we have a certain set of we collect data at it doesn't have a regular time interval or regular um, regular time space when you are collecting just data. But when it comes to time series data, the kind of the definition is uh, data that's collected at regular intervals, but it doesn't have to be regular intervals per se, but as a definition it works, and it's indexed and ordered by the time. So I just wanted to visualize here that the time always flows in one direction, which is kind of obvious when you think about it. But the data will be collected in a regular manner. So in some instances, data might not be collected in a regular manner. For example, let's say uh, a store is selling some product and customers come in, and this product is sold at irregular intervals, right? Because some products you don't sell it every day, so you might have gaps in the middle. So even though that's the case, you can still consider that whole set of transactions over a time period as a time series. Just a few examples here I wanted to show here. So it can range from macroeconomic data such as the inflation rate of a that was this graph was obtained from the Fred site. Then it can go down to the kind of the device level, the device sensor level data. So if you look at the graph on the bottom left, which was collected, which was obtained by a sensor in a water pump. And moving into a kind of a different domain, in medicine, we see these ECGs and EEG data. EEG is where you connect several probes onto a patient's head and kind of read the brain electromagnetic brain waves out of it. And then it is very ubiquitous as well. In our smartphones, we have gyroscopes and accelerometers. So there are apps and devices that can collect this data and kind of analyze this in a time series using time series approaches. So one example is like if you go for a walk or a jog, you might have a app to track your progress, right? Strava or Google Fit or something. So it might use this time series data to see how well you're doing or what activity you're actually doing. Um, if you move on, uh, thinking about the analysis of time series, like traditionally, canonically, the most well-known task is forecasting. This is where you have you look at past data, let's say last year's sales, and try to forecast to the future, uh, what's the expected outcome. Although this has been there for quite some time series forecasting, but it's one of the I believe it's one of the harder fields, because you are always trying to forecast for the future, which I want to make the distinction between a traditional prediction approach, is where you kind of try to interpolate in the data that you already have. So as long as your prediction kind of fits inside that data, it works. In time series forecasting, that might be the case, but usually you try to extrapolate from what from your point onto the future. And other, like, not very well known cases is classification. So classification can be used to kind of identify, like, the operating characteristics of a machine. You might observe its variables such as temperature, vibration, and try to see if it's reaching to a critical point, does need maintenance. Then on a totally other domain, you can use it to for medical diagnosis. So you can feed ECG data into a classifier, and try to diagnose what's happening there, and try to identify, or maybe, since it's medical data, help the doctors make counter diagnosis. And like I mentioned earlier, human activity recognition. This is where you use the gyroscopes or the accelerometer data to see what you're doing. Then I think one important area is anomaly detection. There's a bit of a overlap between anomaly detection and classification as well. So anomaly detection is where you observe a certain time series and try to, when you see some behavior that's kind of out of the normal behavior of this time series, you would try to alert interested party on it. So my go-to example would be here. So you have a cloud system or a computer. Let's say an intruder is now gained access to your system, and doing some kind of illicit activity on it. So let's say he's mining bitcoins or something. So if you didn't catch this on time, it's going to rack up a huge bill. But like, what happens is, if you had some kind of anomaly detection system, it could see, okay, usually compute resources are allocated at, let's say, at 50%. But today there's an anomalous event where it's now it's being utilized up to 80%. So then now the anomaly detection system can alert the users about this. Then clustering is where you try to, so if you have multiple parallel time series or large number of time series, let's say if you go back to a large retailer and you have, like, let's say 100 products or 1,000 products, each product's sale can be represented by an individual time series. Now you might want to fit a model to kind of forecast the sales of these time series, but you don't want to fit individual models for each. So what you can do is you can actually cluster these models together and try to kind of find a common grouping in there, and make a forecast. Then again, time series clustering can also be used to identify what kind of products are, like, has a fast velocity, how fast is it getting sold, and if there's any other products that has, like, a lower value. So that's some application of clustering as well. So when we think about time series, it can be, there can be certain patterns that can be recurring in the time series domain. So we tend to kind of break these patterns into, like, well-known components. So a trend is when you have, like, the time series might have monotonically increasing, or it can be decreasing uh, as well. So if you look at the bottom left graph and the top right graph, these have so the bottom left graph has a trend, increasing trend, and the top right graph has a decreasing trend. Then, if you think about the seasonal pattern, is where a certain pattern occurs due to the seasonal effects of time, right? So, for instance, during Christmas time, as you get closer to 25th of December, the sales of gifts might go up, right? And during summertime, the sales of ice cream might go up. So these are seasonal effects. They can be predicted because you know for a fact that this is influenced by uh, the time of the event occurring. Then we have cyclic patterns, which can be said uh, as an increase and a decrease in the data, uh, but they don't have a fixed frequency or a regular timing as if you have with seasonal data. So these kind of processes or these kinds of like things are kind of driven by external factors that are kind of hard to predict. So that's one example, one thing about cyclic patterns. Usually, when you say seasonal and cyclic, it might be a bit confusing, but always remember when you say seasonal, it's always tied with the time. It could be weekly seasonality. Over the weekend, people might go out a lot than when they are on the weekend, or at a certain point, there might be large amount of traffic during weekdays, and in the weekends, that traffic might be kind of clustered around some other area. So these are seasonal effects, but cyclic effects are something that kind of uh, happens due to other factors such as economic factors, and so on and so forth. So here, the top left graph, it has two of these components. So it has a strong seasonal component shown by these small sign kind of components. Then it has like a larger cyclic component, again, which has like a increase and decrease. So which kind of spans about 1 or 2 years. So we discussed about this. So this bottom left one also has a seasonal component. Then this bottom right one. So this is daily changes in Google closing stock price. So it's not the stock price, but kind of the change. So you take the difference between today's price and the yesterday's price. So this doesn't have any of these components: trend, seasonality, or cyclic nature. So it's what can be kind of quantified as like a residual or a white noise. So when we are doing the analysis, initially we can, as you can see in a little while, we can actually break this down into these individual components and make the analysis on that. Right. So just to kind of build up some intuition on how these models are working. So we'll start with this models called statistical time series models. So in time series, just like any other field that machine learning is kind of has entered, there has been like classical approaches that has worked well up to a certain extent. So right now, what we are going to do is we are going to look at some of these approaches. So autoregressive model is where you try to predict the next time step using as a sum of past time steps. So the kind of intuition that I want to build is, if you have like a traditional regression problem. So this is not a time series problem. This is where you have uh, dependent variable or the y variable that you want to predict. Let's say this is like the price of a house that you want to predict, right? Then you have certain features that you can use to make that prediction using a model. So these features could be how many bathrooms you have, what's the square meter size, and so on and so forth. And there's an error term as well. So this is kind of considered as uh, like uh, amount that can't be modeled, which can't be explained by a model, right? So similar approach we can use for time series, where you are now trying to um, predict the teeth time step t, using a weighted combination or a weighted sum of the previous time steps. So it's a regression model basically, but on its own past components. Instead of these x1, x2, x3 features, it's actually being fitted on its own lag values. And this c and c is as a constant value, which we usually find in regression. And then this is the error term. So this can again be formulated into kind of like a standard formula where we have the AR. So when you say AR, that means auto-regressive. Basically means it's regressing on its own self. So we kind of define these models with the order of the model. So if you say AR3, that means this is looking at lag, 3 lags back. If you say AR1, it's only taking this last term to predict the next term. And if you say ARP, that means it's looking back for P steps to make the prediction on YT. So like when you talk about these AR models, or AR or MA models, which we'll talk about next, one thing that you need to keep in mind is that you have to do something called make the time series stay stationary. So they are kind of expecting this property of stationarity. So the property of stationarity is where you want the you want the you want the statistical properties of the time series not to change as time progresses. So if you look at these graphs, the Google closing price one, it has a clear increasing trend here. So that means the kind of the mean of this distribution, it increases. And so is the case with these egg prices in the US, and this gas production in Australia also. It has an increasing trend. That means the mean is increasing, as well as it has an increasing variance as well. And similarly, the other one graphs has either a seasonality or trend or both. So here actually what can be considered stationary is the change in Google price. If you can remember, in the last graph also we looked at this. So change in the Google stock price, as well as so there's a kind of peculiar graph here, which is the lynx population in Canada, or the lynx fur production in Canada, which is basically example for this cyclic behavior. So they use lynx is kind of a big cat, kind of similar to a bobcat, if you have seen one. So their fur is used for some production work. So here, this, although it looks like a seasonal series, it is not really a seasonal one. It's actually a cyclic one, where the whole cyclic property is dependent on the lynx population. When there's enough food for the lynxes, they can eat, and the population grows. And when the population grows, they get hunted, so the production goes up. Then the population dwindles, and when it goes back, then again they are not being chased. When the population is small, then they have opportunity to grow again. So this is again not kind of dictated by the seasonality or the time, but it's actually dictated by other factors. So that's what the cyclic nature of it. Um, then the other component or other model that we need to look at is the moving average model. So similar scenario like the autoregressive model, but instead of taking the lag values of its own self, instead of doing autoregression, it's smoothing itself using the error terms. So the error term is calculated by getting the actual value and uh, subtracting the predicted value from it. So epsilon t here is the first lags error and the second lags error, and so on and so forth. So similar scenario as previously, and in this model you want to learn this theta 1, theta 2, etc., like in the previous one. So we have now two models to kind of fit time series. So you have the AR and MA models. So you can now we can make combinations of these and to make like models of increasing complexity. So AR and MA gives an AR MA model and AR MA with integration. So integration is where uh, you you have I mentioned earlier, you need to have the series to be stationary for these models to work. So AR and MA. But this AR ARIMA model a kind of handles that part for you as well. It makes that in difference. It's called differencing, where you subtract the next value from the previous value to make it stationary. So it handles the differencing using the ARIMA model. Then you have AR MA with a seasonal component, which comes back to something called Sarima. And the third kind of model is called exponential smoothing, where you get like get a weight average of past values, but it's a weighted average, and the weight gets reduced, gets decayed exponentially as you move away from the point of forecasting. Uh, I'm sorry, I can't see the screen. You guys have, if you have any questions there, please let me know. Hello. I suppose there aren't any questions so far. Uh, so here. So those are the classical approaches that we looked at for the time series. But how can we use machine learning approaches to make the prediction or make forecasts? So one scenario is you have a single series where you have uh, from start to up to t levels. One thing you can do is you can kind of pivot this and put the yt value or the value that you want to predict as the y value, and the other lags or lag values as x values, kind of similar to the autoregression model. And you can kind of slide this over and make several samples out of this. But you need to keep in mind, when you slide it over, it kind of gets it kind of gets filled by empty values on this side. One thing to keep in note so far on this is that one thing to keep in mind is that when you are applying like a traditional machine learning model, let's say if it could be XGBoost or random forest, it is important to not to mix up this whole test and train split. So what I mean by that is you have to be mindful of the direction of the time, and when you are making that split, you have to be kind of mindful so that data from the actual future doesn't get incorporated into the past. It doesn't get fit into the training model. So this although this kind of sounds simple, it's something very easy for you to kind of slip up and make a mistake. And if you're familiar with cross validation, again, this is where how you can do it. Like you fit the training model and you have the test. Now you move that window by a step size forward, and you can never come back and go on with the cross validation. Then there's another approach. Since like when you're dealing with time series, you might not have like large amounts of data, so it might be a good idea to kind of leverage all the data you have. So here it's kind of going from uh, training to test. Then what you do is, instead of sliding this window, you are kind of expanding the horizon of this training window and moving forward. So those are some of the things that you kind of need to keep in mind when dealing with time series data, and when you are trying to use machine learning models such as um, uh, ridge regression, elastic net, or basically some things that you would use in the sklearn package. You can use them, but you have to be mindful of this. Uh, so so that's about like machine learning in general. But what's happening with the deep learning space? uh, Recently there's been quite some like interest in deep learning researchers to apply time apply their techniques to time series. I think the main obstacle would have been the lack of data, because again, when you are dealing with time series data, if you're collecting something daily, if you're collecting a metric daily, at the end of 1 year you will only have 360 365 such data points. If you have like large number of parallel such series, maybe now you can do something with deep learning. So that's where kind of these newer approaches kind of had come through. So deep AR is a approach that was developed by Amazon Research, AWS. I think it kind of fits their business as well, because Amazon has that kind of data that I'm talking about, where you have like large number of product SKUs and their sales kind of spanning like a time series. And so ESRNN is a method developed by someone called Slavik Ismail from Uber. So this is where you're using a hybrid, what's called a hybrid approach. You have an exponential smoothing model, the one that we talked a little while ago, that is feeding into an RNN network, and you're learning the exponential smoothing weights as well as the RNN weights in unison. Then there are other approaches such as MQRNN, again something that was output from AWS. Then Google Research kind of came up with a method to bring in other variables, the exogenous variables. For instance, you might have the time series. Let's say you are predicting the ice cream sales. Now you can bring in another variable such as temperature, mean temperature, into the mix to kind of make a prediction. And you can bring in other categorical variables as well. Then kind of different. So all these methods are using what's called an LSTM or RNNs. So LSTMs are kind of like a more improved version of RNNs, because RNNs kind of have a problem with long sequences, remembering long sequences, and LSTMs are inherently able to kind of retain long memory over a period of time. But this NBITS, one that's kind of developed with Oreshkin in conjunction with Yoshua Bengio, is a model where you're using like a stacked, fully connected neural networks to make predictions. So it's making these it's kind of breaking the full time series into components and trying to make those predictions in individual and finally add them together towards the end. So what we can usually generally see is these kinds of deep learning methods might apply to large sets of time series data. So it's not only one time series. This data might be spanning like several years, as well as the scale is so big. It might be thousands of time series. So it might not be practical to fit individual ARIMA models for each time series. So because of that reason, almost all of these models, except for NBeats, is kind of trying to build global models to kind of cross-learn across time series and make those predictions. Uh, in day-to-day, or I suppose in more often than not, in your career, if you are a data scientist, chances of having to deal with this kind of model might be low. You are kind of better off kind of focusing on the classical ARIMA and classical approaches, as well as dealing with this machine learning approaches such as the tree-based and boosting approaches. So that's it for the presentation portion. Let me quickly. Tiara, you can still hear me, right?
Tihara is not there. I'm here. We can
Sure.
hear you.
Yeah,
Yeah.
just checking. Right. So let me walk you through a couple of examples here. So what I wanted to kind of introduce you to the kind of basic theory, but even like what I believe, although I put it there in the slide, it's kind of not something that you can get in one go. But I'll share this uh, notebook as well to kind of deal with like a I would say like a practical problem. So I have already run this notebook. Let me walk you through what I have done so far. So if you're not familiar with this environment, this is called Google Colab. Yeah, and if you're someone who's interested in getting to know data science and ML, maybe something that you should definitely check out, because this has a computing environment as well as uh, uh, high performance GPUs and as such. So in the first cell, what I'm doing is I'm installing this package called SKTime. So SKTime is an interesting package because it's kind of a one-stop shop for all your time series needs. Mainly because it's in most of the scenarios, it's a wrapper around these well-known time series libraries. And at the same time, it has its own unique approaches that kind of makes life easier. It follows the sklearn philosophy of the whole fit transform functions and predict functions. They're kind of familiar with to someone who has already familiar with those things. So I'm then importing some of these packages, and here I'm setting the kind of aesthetic stuff using Seaborn, which is a plotting library. So this load airlines function is something that I imported here. It's an inbuilt function in SKTime to kind of give us a feel about what kind of data that can be dealt with here. So this is a airline passenger booking data set. If you load it and if you plot it, it looks like this. So it's a monthly data set, kind of shows how the kind of the growth of the airline passengers over time. And so as an initial thing, I think one of the important things you can do initially also is to kind of plot the data and see what's going on. This is something kind of unique to like time series, maybe in regression problems in general, but you can learn a lot. For instance, you can see it has a trend. It has a increasing variance as well, definitely not stationary. And it has a seasonal factor as well. What I'm now doing is here I'm kind of setting the date axis in the data frame. So I have read the data frame. So this period is the month. Then what I'm doing is I'm decomposing this into that the trend, seasonal, and we are not plotting the cyclic, but we are plotting something called residual. So cyclic component is kind of it's kind of taken as one as part of this trend. But residual is, so we have, this is the original series. Now we break it down into the trend. Then we have the seasonal component. What the other part that can't be explained from these two components is shown as the residual, right? Right. Then the next analysis we can do is kind of look at what is called autocorrelations. So autocorrelations is, again, if you know what correlations is, if you have two variables, how much they are connected. Like if you increase one variable, how much effect it has on the second variable. So that's correlation. Autocorrelation means how much influence one time step has on the next time step. So whenever we put this word auto in there, auto regression, auto correlation.
Manik,
Sorry.
sorry to interrupt. Um, I think it's good if we can zoom it a bit more.
Hmm. Give me a second. I guess I'll use this. Is this good enough?
Yeah, yeah, great.
Right. So what's meant by autocorrelation is, so you have the yt step and the yt minus one step. How much of an effect does yt minus one step has for the yt step, right? Now, if you look at here, you can see this is the first value, and the second lag. So this is not exact. These are not the exact values in the time series, but kind of the lags of those. So that means if for a given value, the value immediately next to it has a high correlation to it, and the value after that has a lower correlation but still significant. This shaded area is what's known as the confidence interval. Whatever spike that comes above this shaded area can be taken as a significant, like a statistically significant effect. So all these values are highly correlated. I wouldn't say highly, but some of these are highly correlated with the first with the first value. So that means for a given value, one step back has a high correlation, two steps back has a high correlation, three steps back has a high correlation. Likewise, you can go up to, I think, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 steps, 14, right? But when we say this, there can be a situation where this value is affected by the step next to it, but this one has an effect. So this yt minus 2 has an effect on yt minus 1 as well. So how do we kind of filter out the that effect? So that's why we kind of plot the what's known as partial autocorrelation. Now you can see, although this has so many autocorrelations, with partial autocorrelation, it kind of gives the pure effect on this first value. So obviously the one next to it is highly correlated with it. But apart from that, only a handful of values are correlated with this value. So why are we interested in finding if it's correlated? Mainly because the auto-regression AR models or the auto-regression models are kind of banking on this fact that if it's correlated, it can kind of build a pattern on it, and it's kind of, as you can see in a little while, it's kind of significant that you need to identify what's the how many lags back has the bigger effect. If you move forward, so now what I'm doing is I'm using this function called temporal train test split. So this is a function provided by SK time, which I think is important because I mentioned earlier, you can't poison your train data, right? So this temporal train test split kind of ensures that it looks at the time axis and makes sure that what's in the future doesn't really come leak back into the train set. So I'm using that to split it. Let's see if it. Let me show you what why train and Okay. So tail means uh, I'm looking at the end of that value, and I'm going to look at the head of y test. So then these should have corresponding. So this is 1957 December, and test set started from 1958 January. So that it's kind of cleanly split it from that point. Then I'm fitting an ARIMA model. So ARIMA, again, a combination of AR, MA, and the differencing, because we are not dealing with stationary data. So initially I try with just a simple ARIMA model, and I get a mean absolute percentage error. Not that, because this is an error, the lower the error, it's better, right? So we get a significantly lower. So this is like 11%, 11.94%. But if you actually plot this, this should be observed, or the true value. Sorry, I think I messed up. That's a okay. So it's not that great, right? So we have the observed values kind of with this pattern, but the ARIMA is just fitting a straight line, which gives a, I mean, it's okay, but not so great. Then I suppose one thing we can try is, let's look at this autocorrelation plot again. Let's look at the partial autocorrelation, see what this value is. This is actually 13. So if you look at 13 steps back at each point, it has a significant correlation with the value we want to predict. So because of that, I'm building now an ARIMA model of order, the P order as 13 and the differencing as 1, but the Q or the MA model, I have put 0. That means we are not doing moving average here. If you fit this, the model goes down to about 42%, and it's a better fit, but not the best fit in the world, mainly because this series, if you observe it, it kind of has what's known as heteroscedasticity, which is the increasing variance as it goes. So it's not the ideal scenario. Just to kind of get a feel of what works. So this is a bit of trial and error, intuition, as well as driven by theory as well. So this has a significant seasonal component. So the seasonal pattern you provide, so this is the seasonal parameter here. So I'm repeating the 310 instead of the 1310 that I fit earlier. But the seasonal order, I'm just putting 21, and the seasonal period, I'm setting to 12. Which what the seasonal period means is, within a year, how many seasonal periods can you see? So if I set it to 12, that means I'm looking at monthly seasonality. But if you, let's say, have a weekly seasonality, or you need to set this to 52, because you have 52 weeks in a year. And if it's quarterly, you should set it to 4. Again, if I fit it, it kind of comes down to 0.45, which is 4.5%, which is, I think, a good number to have. And finally, so this is a improvement on ARIMA using SARIMA, which is a seasonal ARIMA model. Then we have the STL forecaster. STL means, if you can remember, initially we did this decomposition into the season trend and the residuals. Sorry, here these components. So STL forecast is trying to model those components individually and build that forecast in the end. Unfortunately, it didn't fare very well. Here I'm setting the STL forecast and the seasonal pattern to 12 and setting it to 0.05. And finally, so there's a approach called auto ARIMA as well. So for us to do this, we need to kind of do this whole dance with, setting the p parameter, setting the I parameter and the q. So as people working on with Python, we are interested in automating things. So AutoArima kind of does a search for you on what's the best model, or what are the best parameters, and it fits this, and it brings down the error to about 4.1%. Yeah, so that's kind of an example. That's kind of an example on what can be done with the SK time approach. So this has both the classical and approaches to kind of make your models, make the sklearn models deal with time series as well. I think we have 10 minutes left, right? Hello. I think there are some questions. So one question is, okay, here work with seasonal trends. Is there something additional to do include season? I think AR on itself doesn't. We need to bring in the seasonal component with the seasonal Sarima, basically. So I think Rajit Amar Singh asked if AWS is working with F1. Do you mean as in F1 the racing? Not sure about that. Where have you collect? Where have you a huge collection? Okay. Let me share this. So I have another notebook, but I don't think we have time to go through it. Chamat, what do you think?
Yeah, you can have some time, I think.
Sure. Okay. How do I make this question? Yes. When you run AutoArima, is there a way to find the final parameters it used? There is. Let me. So if I run AutoArima here, I can't remember the exact. You can see the screen, right? Right. So these are the parameters it was set for. So order is the Arima parameters, and the seasonal order is the actually it hasn't really taken the seasonal. It hasn't fit the model that it found. It hasn't. It has put all the values for 0. Let me quickly go through the other one I created. So here, the idea was to kind of give an understanding of how to use this using the kind of sklearn and the traditional ML kind of stuff. I think the previous data set was kind of a bit too easy. It's not very representative of the real world. I'm using here an electricity demand data set, which has like I mentioned, a parallel set of individual time series, but I'm taking just one series out of it to make this univariate case. If you look at it, it has a very high data density. I think the series starts from here, but the data frequency is at 15 minutes time, right? So every 15 minutes a value was collected. So in this scenario from 2012 to 2015, which is like a ton of data, since I didn't want to spend too much time, I kind of trimmed it from. So I'm looking at this full spectrum, and here what I'm doing is I'm resampling the data to a daily frequency. And when you're doing this, you need to be mindful. So what when you say resampling, you have 15 minutes data. Now you are turning it into daily data or hourly data. So since this is temperature, I took the mean of it. But if it's something other than that, let's say if it's number of people that came into a, let's say, a shop, I suppose you can take the mean, but you might be more interested in getting the sum of it. So you need to be mindful of what you want here. And so this is kind of the full series of that. Then I am taking that temporal train test bit, but since this is a very quite big one, I'm just taking a 10% as the test scenario. Again, doing a seasonal or temporal decomposition, you can see there's no clear trend here, right? It has like a large, I suppose you can call it a seasonal one, and the seasonal component is also, I think this is daily seasonality, that because it's very high frequency and significant number of residuals as well. Initially what I tried was took the random forest regressor. So random forest regressor is coming from the sklearn package, if you are familiar with it. And what you need to do is now to deal with this, I think in one of my slides I showed, you have a time series data set. What one way you can deal with this, kind of pivot this data, and just a bit of manual work involved, and it's easy for us to kind of get it wrong. So this make reduction is a kind of a wrapper or a decorator around this random forest regressor, or any regressor that SKTime supports. Kind of gives us a more estimator that can kind of fit to time series data on its own. So I'm using the train, and FH is kind of the it's called forecasting horizon, derived from the test set, and it's not good at all, because this is, again, if you look at this, that there isn't a lot of trend, but it should ideally capture this seasonality, right? Then what I tried was with this. So instead of only using the auto regressive or the time series data, I'm bringing in another variables that are available to me. So in this scenario, what I'm doing is I take this date feature and kind of break it down into different components. So I'm trying to kind of feature engineer some features out of this, so quarter of year, month of year, week of year, and I'm kind of breaking it out from this individual dates. So that's what's happening here with this date features. So I'm fit and transform it on the train data, but on the X date set, I'm just transforming it, because ideally we need to use this fit to transform this, because this is the X test data. This is something that's not available to you at the time of prediction. As in, like, in real world, you don't know what kind of data you're going to get, right, when you're fitting the model. Then SKTime has a kind of handy feature where you have pipelines similar to what we have in sklearn. So you can take the min-max scaler from sklearn and kind of convert it into a tabular to series adapter. So it's an adapter that turns it into a min-max scaler. I'm getting the XGBoost regressor, and making a reduction with a window length of 60, and as a pre-processing step using the min-max scaler. Then using those, and I'm fitting the data here. Instead of setting the only the y value, which I did with earlier models. I'm now passing these exogenous variables that I calculated. Then I made a prediction, which kind of came back to 7%, which I think is a achievement I can be proud of, because it's actually looking at a very large forecasting horizon. This is coming from September of 2014 up till the January of 2015. And as you can see, in the initial stages at least, it's a good fit. But this is a case with time series. The further you go, because the only last available data is from this point, from it's cut off from the September of this year, right? And as a last trick from out of my sleeve, I think most of you already know about this. There's a package developed by Facebook called Prophet, which kind of expects your data to have a certain format. Let's see. So it should have a column called BS and another column called sorry, let me do this. It has to have a column called DS and another column called Y. Then you need to call what's called a future data frame. I'm setting it to 60. That means 60 days ahead, and I'm making the prediction. Here, these black dots are what's available to us, the training set, and this is the prediction set. So this doesn't really we did a lot of comparisons earlier. This doesn't really give us much quantification of like the performance of the model. But what we can do is we can do a cross validation. Here we are what we're doing is we're saying, okay, as the initial window takes 730 days, which is like I think close to 2 years. Then make predictions for 60 days. So at each step, you are predicting 60 days ahead. Then slide that window by 30 days. So with that, these are the values. So one nice thing about Prophet is not only it gives you the estimates for the predictions, but it's also giving you kind of the upper and lower bounds, which is kind of handy when you want to quantify the uncertainty intervals. And here we can see with performance metrics, you pass the CV object into that. You can get a plethora of metrics. So MAPE is the one that we were looking at. So this is gone to 4%, and as time progresses, it has gone to I think 5%. And coverage kind of gives you how much of coverage, how much the prediction interval is covering this, how much of percentage. And this is a plot of the MAPE values, which is kind of moving from below 5% up to I think 10%. Yeah. And similarly, this is the SMAP, which is the symmetric MAP. Yeah. So that's about it for this one. Any further questions? Okay, Taraka Vijayaratna asked if I missed when you say how to select seasonal parameters in ARIMA. So I think it kind of comes down to there's a way to actually quantify the seasonality as well. But if you look at it, if you look at the plots, you can see what kind of seasonality is there, right? So if the event you are interested in is it occurring monthly, then your seasonality should be 12, because within a year there are 12 months. So seasonality is always in respect to the full year. Then if it's quarterly, it should be 4. And if it's daily seasonality, I don't know if these older models kind of can go to that level, but I think Prophet can go up to daily seasonality. It should be, I think, 365. Hope that helped. Let me share this, share the link to these notebooks. Uh, if you, I'll just post it here in the chat, right?
Okay. We will share these things in our channels. Then they
Sure.
can grab them.
So have a look. I'm sure there might be ways to improve it. Please give some feedback if you see any mistakes. Uh, so I just wanted to like give a feel about how to, like, on two accounts, like kind of the toy problem and actual real world thing as well. And if you have any further questions, happy to take them. If not, we can conclude.
It's about to wind up the session, guys. If you have any question, please feel free to ask them in Q&A tab or in just in a message.
Uh, Right. So I think Yahan is asking if this can be used to predict stock market or crypto. Uh, I'm I'm not too kind of confident about those kinds of things. But if anyone is interested, there's a guy who's kind of doing similar thing where he has a. I mean, it's a online competition basically. Let me share the link for that as well. So So the nice thing is, unlike Kaggle, this is an ongoing thing where you can make predictions real time, and your model will be evaluated in real time as well. I think more than competing, there might be things that you can actually learn out of it. I hope I make predictions. So he has an API that you can build a model and submit, and you can make predictions on it as well. On the matter of crypto and uh, stock market, I feel like there's a bit of large amount of stochastic behavior in that, so might not be ideal. I mean, that's something that's an age-old problem that people try to predict, but I suppose with varying success. Um, if you make a breakthrough, please let us know as well.
I think that's about when like we are running out of time.
Yes.
So, Manik, can you please share some contact information if
So
anyone
in the chat itself,
yeah, sure, we can add
uh,
them to the other channels too.
right? Let me get my so on LinkedIn. Let me put down my email address here. So if you have any questions, or if you need any help with anything, I'm happy to help out. And this is the first time I'm joining the Python community. Looking forward to the next sessions.
Yeah, I think that was a really great session, Manik, and we are just starting with these things, and we'll be able to gather more people around our sessions in future. So, and thank you very much for your time with us. And I think we was able to like get an idea about how to do these things with Python and using how to use Colab and those things. And that was a very valuable session. So thank you very much again. And yeah, sure. We'll be able to contact you in future sessions too, I think. So if you're free. So guys, if you have any question, please feel free to contact Manik. So I think it's time to wind up this session. So thank you very much, Manik, again, and let's have a great day.
You
Bye,
too, and
guys.
thank you for inviting me. Thank you. Bye.